Right, take your time starting recording. Here we go. A while ago, some flurfer was talking about perspective and getting it wrong, and I offered to explain how perspective works using brightly coloured chalks, because I thought, black and white lines and long quadrisyllabic words might be a little bit intimidating, but keep it comfortable, pastel tones, colourful chalk. So why have I got a black and white line diagram with all these decimal places and long words in it? Because flurfers. No, actually, I've got this to explain some terms. What we have at the top is an equilateral triangle, 60 degrees in each corner. I have split it up the middle with a line which meets this side at a right angle and exactly bisects it. Whatever distance this is the same distance. These sides are twice this distance. If this distance is 1 inch, this is also 1 inch. This side is 2 inches. This side is 2 inches. If this side is 1 kilometre, if this distance here is 1 kilometre, then this is also 1 kilometre, and this distance down here is 2 kilometres. This distance we can tell from Pythagoras' theorem. That squared plus this squared equals that squared. 1 plus this squared equals 4. That is root 3. From there down to there. This triangle will come back later. This is another right angle triangle which may be familiar. 5, 12, 13. 25 plus 144 is 169. Pythagoras again. The angle down here isn't anything as neat as 30 degrees. It's 22 points. Blah, 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 blah. A lot of decimal places. But this gives me a nice big space in which to show. From that angle, this side at the opposite end of the triangle is the opposite. The side opposite the angle is the opposite. That's fairly obvious. The adjacent side next to this, adjacent to it, is the adjacent. This is a right angle. And if those two were wooden beams, steel bars, whatever, holding a wire under tension, it would be hypo, under, tenuse, tension. This longer side is the hypotenuse. And three things that will come up. SIN is not that thing you have to tell the preacher about on Sunday morning. It is an abbreviation of sine. It is the ratio of the opposite and the hypotenuse. Specifically, the opposite divided by the hypotenuse. In this case, it is 0.384. Cos, not a kind of lettuce, cosine. It is the adjacent divided by the hypotenuse. And I have put equals 0.923 in the wrong place. It should be down here next to cosine, not up there under hypotenuse. It's easy to make mistakes like that when you're casually doing diagrams late at night. The tangent is the opposite divided by the adjacent. And in this case, 0.41 and a heck of a lot of 6's. 5/12. These terms will be coming back later. Not this one so much. These two, definitely. That one does show up when I'm doing Earth curvature calculations. These two will be coming up in the perspective discussion. So that's your diagram with scary long words and scary long numbers in the wrong place, and harsh black and white lines and little angle symbols and things. And GIMP doesn't like you trying to do the degree symbol, so those are hand-drawn degree symbols. Scruffy, aren't they? Anyway, I did offer, brightly coloured chalks, so let's get to some pastel colours and brightly coloured chalks. This here is 6 sheets of paper, with obviously a join between them down there, and 2 joins there and there. They have 3 points marked. That one in the distance, that one there, that one here. And you can see on the screen that on the screen they appear to taper into the distance. This is probably not an unfamiliar effect. This is perspective. You can also see on the screen that the angular size, the width of the screen taken up by this nearest sheet of paper, is greater than the width taken up by the same length of the second sheet, and that's greater than the width taken up by the same length of the third sheet. Again, due to perspective. I'm very close to the pieces of paper when I took this image, so there's proximity distortion, if you want a term for it, going on. But this is a setup that may be familiar if you've studied drawing at any point. From 1 point perspective. Why 3 points? Well, this is the 1 point. The vanishing point directly in front of the viewer when you look at this drawing square on from the correct position. These two would be chosen so that when someone stands in the gallery and looks at this drawing on the wall from a very specific point in the gallery, each of these points is 45 degrees out to the side. So all the lines going from the viewer's position off into the distance in the direction they're looking are going towards this vanishing point. Any line that's going off at 45 degrees to those lines is going to one of these two. Also faintly visible from here, down to here, down to here, and up to here, I have drawn a rectangle, and I've marked it at 2 centimetre intervals all around the edge. It's not actually a multiple of 2 centimetres tall, so there's a slightly funky bit in one corner, but apart from that, it's at 2 centimetre intervals all the way around. Sorry, in each of these two corners there's a little tiny fraction of a centimetre gap. Using this thing you can see at the end there, which is a steel ruler. It's probably not perfectly straight, and of course my pencil is not perfectly sharp, and my eyes are not perfect, and these sheets of paper aren't perfectly lined up, so there are always going to be approximations in this drawing. This is the setup. Here's a square view of it, looking straight down on that central vanishing point in the middle here, with the grid rectangle around, and I've flipped this to get the funky bit in the top corner out of the way. That's just a close-up of the grid in the corner, pre-flip, so these are 2 centimetre intervals from that corner that way and from the same corner this way. Doesn't look square on the screen because of perspective. And here are lines from those points around the edge to the vanishing point. Not from all of them. I didn't bother drawing the ones in this gap here. I didn't bother drawing them in on this side. But we have lines from this edge, which is at the top of the screen, from this line here going off somewhere to the left, all the way across to this line here from the corner, and then down the side from the corner all the way down to this line here, all going to the vanishing point, and lines from the opposite side also going there. Straight lines to, well, not exactly to the vanishing point, because obviously it's a big blobby star drawn with a Sharpie, and it's not an exact point, and my eyes aren't perfect, the pencil wasn't perfectly sharp, etc. Pretty close to it. There is inaccuracy here, but out here they're pretty good. The same margin of error is a very small percentage of 2 centimetres compared to what it is down there. This is that ruler laid across the lines. Down here the lines are 2 centimetres apart. The ends of the lines are 2 centimetres apart, so along this they are 2 centimetres apart. Where the ruler is, they are 1 centimetre apart along its top edge, which is halfway from this bottom line to this crease. On the paper, halfway to the vanishing point. In the three-dimensional space represented in a drawing on the paper, nothing like halfway. And now I've done some arbitrary blocky shapes. 2 blocky shapes just touching here. Not quite rotational symmetry, just touching. A shape with a space in it, a window. Another shape with a little bit propping it up there so it doesn't collapse under its own weight. And a repeat of the second shape here, so I can do the two slightly differently. And they did promise bright coloured chalks. There you go, brightly coloured chalks. Orange on top, purple on the face, green on the left, blue on the right, which you can't see on this one. And in here I have done lines from all the corners, where you can see them, to the vanishing point, or somewhere very near it. Just all the way there and shaded in. So this thing is just going off straight for whatever distance this is to there. I'll come back to that. That's very simple. Probably looks familiar from early 1980s superhero movies. It's just a shape off into the distance. Here's the other one of those shapes, but I have terminated it here. I just put the ruler across at an arbitrary distance and drew a line across there. Where it crosses this line, stretching off towards the vanishing point, is where this corner of the top surface is. Where it crosses this line, stretching off to the vanishing point, is this corner of the top surface. A line vertical on the paper, down from there, intersects this line, to give me this side, shaded blue, and horizontal from there to where it intersects this line, gives me this upper surface, shaded orange, and vertically down from there to this line, gives me another right side, again shaded blue. And you can see the window. This is just an arbitrary length. It's just this, but sliced off, perpendicular to the direction of view at an arbitrary distance. What if I want to make it a very specific distance? What if I want to make it out of cubes? Well, here's where this shape comes in, this 5-like shape here. You can see, faintly, here, 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 and here, I have marked points vertically above these points on the bottom edge. And from those points, I've done lines going off this way. To that right-hand vanishing point, and this way to the left-hand vanishing point. And as I said, those are 45-degree lines, which means those two distances are equal. This is a 1, 1, root 2 triangle. So that is a square, and that is a cube. And this is a 5 by 4 by 1 shape with some spaces in it. Same thickness as the height of that and the width of that. And I can do that on a larger scale here, going from this corner, this top left front corner, off to the right hand vanishing point, gives me this 4-unit width back from the top right vanishing point, where it intersects that line. Back from the top right point of the front face, back to the central vanishing point, there intersects the line from the top left corner of the front face to the right hand vanishing point, going this way, at that point, making this a 4 by 4 square, and this whole shape a 4 by 4 by 5 cuboid. I've got another diagonal from there, going off to the left vanishing point, meeting this line to the central vanishing point there, which gives me the back left corner, and where it intersects this line to the central vanishing point gives me an inner corner, so I have a 1 width perimeter here, both sides and across the back of this cutout, this sort of chair effect. So we can do 3-dimensional shapes, and if you're really bored and you have nothing but a pen, a ruler and a huge piece of paper and a flat place to work, you can do really massive elaborate shapes like this just to pass the time if you really want to. Or if you're in art school, you can call it practice for perspective drawing. You may notice that while this shape, this 5-like thing, looks fairly reasonable, this one might look slightly distorted. And further away from this vanishing point you get, the more distorted they look. Reason for that, which is that I'm using straight lines, and they shouldn't quite be straight. Here, you wouldn't be able to tell the difference, but the further away you get, the more it starts to matter. Here's another arbitrary blocky shape in another corner. It's a 7 by 7 with 4 2 by 2 spaces in it. The pencil is pointing at the intersection of the line from this inner corner to the central vanishing point and the line from this inner corner to the right hand vanishing point, which makes this shape a 5, 5 and 5 root 2, which is about 7 triangle. And horizontally across from there to where it intersects the line from there to the central vanishing point would make a 5 by 5 square. That allows me to extend this shape. Oh, hello. Here is another diagonal going off to the right hand vanishing point, another line from here to a central vanishing point, making a 1 by 1 by root 2 triangle for a single thickness. These two allow me to create a 7 by 7 by 1 shape with 4 2 by 2 by 1 spaces in it. Using this one for the thickness, and using this one, which is where the pencil is pointing, I can give it this space. This is a 5 long space in the middle, making this a 5 by 2 rectangle, or a 5 by 2 by 1 cuboid if you want to include its depth, and this another of the same. And I can repeat that. This is a close-up on the underside showing the diagonal from bottom left front corner through the corner of one window, through the corner of the next window to bottom right back corner of a 7 by 7 by 7 cube. But I can extend it further than that. I can make it a 13 by 7 by 7 cuboid with a set of 4 5 by 2 rectangular spaces in its side. And what I've put here in bright green are pixel counts. The height here 1760, the height back there only 1054. Or, if you want to do that mathematically, 1760 here, 1054 back there. And the pixel count widths of these windows, 237 here, 146 back here. As it gets further away, it takes up less and less of the paper. That's not really news to anyone. Big question is, why those numbers? That's just the same drawing without the numbers. Who cares? This is a different form of perspective drawing. I'm using almost the same 3 vanishing points. That's the central one, and the other 2 are way off to the sides, again. You can see lines down here angling off to the left, lines down here angling off to the right. The vanishing points are out there. Instead of doing all my blocky shapes with their orthographic lines, sorry conspiracy cats, pointing at this distant vanishing point in the centre, and the diagonals pointing 45 degrees off to the side, I've got my orthographic lines, sorry conspiracy cats, pointing to 45 degrees off to each side, and the diagonals pointing at that vanishing point. There are diagonals and all kinds of weird lines drawn on this. This is a diagonal from the bottom of the front edge to the top of the left-hand edge. Diagonal from the bottom of the front edge to the top of the right-hand edge, and so on. It's an arbitrary size, it's not a multiple of anything in particular. These extra lines in the middle are where I was going to draw in more slices of stuff, but honestly I just got fed up with drawing lines and using that ruler and so on. So I just stopped with this simple outline cuboid frame with rectangular section bases and square section uprights. I did bother to square section the uprights. So we come to the question of why those sizes on the paper. Here is a side view, an orthographic view, sorry conspiracy cats, of a whole bunch of lines. Great. You can think of this as a map, if you want to, of 2 very long walls going off into the distance there and there, in parallel, with another wall in between them here, also parallel to them, a camera position here. The camera is drawn in not to scale, otherwise those would be very, very small walls. And walls across at right angles to, orthographic to, sorry conspiracy cats, those walls, there and there. Walls form fences, so they have fence posts. Here, 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 and here. And here, here, and here. And at these positions along here. And along the top. These are at 1 centimetre intervals on the paper. If anyone wants to reproduce this using 2 sheets of A4 and a steel ruler, 1 centimetre intervals, and I can't tell you exactly how many centimetres long this is, I forget. Doesn't really matter, you can get something very similar and you'll see the same effect. From these points along this line, stretching into the distance on the left, from this cameraman's point of view, I've drawn lines to the viewer's position. All of these lines. I stopped there and started again out here with just 3 lines from there, and took a break and drew another 3 from all the way out there in the distance. All of those lines are coming back here. So we have this straight line across, and there is a series of lines there and continued there and there from this left-hand wall. I've done the same thing but not as many lines from the right-hand wall, just there and there. So that series of lines and that series of lines, just there, are part of a series coming this way, which is a reflection of the series coming this way, that is all of them. I've also got lines from the distant cross fence, from this corner if you want to include that, and from these 5 points coming back. So the bottom of this group, I apologize, the bottom of this group of 3 lines, and 5 lines below it are another series of lines from a thing viewed at right angles here. And I've got 3 lines from here, from this crossways fence. So these 3 lines here, here, and here on the paper, on this line across, are from a much closer crossways fence. And in this central wall going to the distance, I have marked those 3 points, those 3 points, those 3 points, and those 3 points, and done lines back from all of them. So just here, from there to there, we have lines from a wall that's just slightly off to your right, going off into the distance. And I'll give you a close-up of where all of these lines cross this line, with an extra bit of detail drawn in. This is that crossways line. If you were doing a landscape view of that view down 3 parallel walls, the couple of fences across, this would be the proportions you would have to use for their positions. So this is the start of what was the bottom is now the right hand series of lines, and this is its continuation in the distance. These 3 are from that near crossways fence. All of these, and that group of 3 lines there, and that group of 3 lines there, are from the left hand, way off to the left, wall going to the distance. Those are parts of the same series of lines, and this set and this are part of the equivalent series on the other side. So you have symmetry there. Approximately this group, and this group, and that set, and that set. And if I go back one, you can see all of these from this central wall blur down into just one thing. So it looks like just 3 lines there. That is actually 2 sets of 3 lines from that distant part of the wall, and these are from the closer part of it. They get that much closer together because it is a long way away and near the centre of your field of view. Meanwhile, this set of 5 and this set of 3 are the lines from the crossways fences. Drawn on paper, they would be along this line and along here. Same line, just different parts of it, because you draw different things on different parts of the paper. In terms of angular size, it's on this arc, which is not quite the same thing, but you can see in both cases that the angles between them get smaller as they go into the distance there and there, and that the angular sizes of the gaps between the posts on the distant fence are less than the angular sizes of the gaps between posts on the near fence, and that the angular sizes of posts along a wall going away from you near the centre of your field of view are less than the angular sizes of the gaps between posts along a wall going off into the distance where you're looking further out to your right or left. So the same decrease in angular size with increasing distance is happening, and that brings us back to right-angled triangles. If you're looking at a thing at right angles, you could be looking at the centre of it at right angles like this, or at the base of it at a right angle like that, assuming of course that you're free floating level with the base of it, or you're on a completely flat plane, or you're at an elevated height which is in effect level with the base of it. And in this case, its angular size here, well, that's its actual height. If you're level with the base of a building and a long way off, this is your distance from the base of it. And this is the height of the building. And this angle will have a tangent of the height of the building divided by your distance from it. If you're looking at a flat object square on at its centre, its angular size is the full width of this arc, which in this case is 60 degrees, because that's my equilateral triangle from before. And everyone knows that an equilateral triangle has 60-degree angles in all corners, don't we? Yes. That is twice the angle here, the tangent of which is half the width of the object divided by your distance to it. So angular size is twice arctan half the width over the distance. Here's an illustration of that. The angular size of USS Enterprise here will be twice the angle which has a tangent of half its width divided by the distance ahead of it at which you're looking at it. With a circular object it's slightly different. Because you can't actually see this point here at the side, it's obscured by this point here, not quite out at the side. You're not looking at a diameter of the object. You're looking at 2 points that are slightly nearer than that. And the right angle isn't here in the centre. The right angle is here. You are looking along 2 tangents to the circle. We use tangent to mean 2 different things, just to annoy you. Those are simply lines that are at right angles to the radii of the circle. So you're looking at right angled triangles that have their hypotenuses together, and the distance here is therefore the hypotenuse of the triangle, not the adjacent. So if you measure this angle, or you know this radius, or you know this distance, the relationship is that this whole angle is twice the angle in here. The angular size is twice this angle, which has a sine of the radius of the sphere divided by the distance to its centre. Distance to its surface, just work it out. Don't ask for a formula for that one, I can't be bothered. Twice the arc sine of the radius over the distance, rather than twice the arc tan of half the width over the distance. At very great distances, there's very little difference. At shorter ranges, it does matter. Take, for example, Grenfell Tower. Grenfell Tower was a place where lots of poor people used to live, and the rich people living in a more expensive part of London thought it was ugly and spoiling their view, so they wrapped it in plastic, which turned out to be flammable, and it killed lots of people. Therefore, this is an example of a tall thing which somebody wanted to disappear. If you want Grenfell Tower to disappear simply by being so far away that you can't see it, well, I would suggest moving to Austria. If you want to live somewhere, with a line of sight to it, and you want it to be so far away it has an angular size of 0 and therefore can't be seen, you need its angular size, this angle here, to be 0. That means you need the tangent of the angle to be the tangent of 0, which is 0. You need its height divided by this distance to be 0. How far away do you need to be? Well, there's another way to look at that, which is this angle. Between vertical where you are, or rather parallel to the building where you are, which isn't vertical for reasons having to do with globe, you have an angle here of 90 degrees. So whatever this angle is 90 degrees minus the angular size of the building. If you want this to be 0, this must be 90 degrees. So this distance here divided by the height of the building, it's the same distance because this is a rectangle, divided by the height of the building must be the tangent of 90 degrees. If you want the sun to disappear from view due to being too far away to see and having an angular size of 0, you want this angle between the two sloping lines on your screen to be 0, which means you want the angle between each of those sloping lines and the central horizontal line to the centre of the sun to be half of 0, which is 0, which means you need this distance, this straight line across the middle of the screen from viewing position to centre of sun, to be so great that the radius of the sun divided by that distance equals 0. And if you're into algebra, sine is opposite over hypotenuse. Multiply both sides by the hypotenuse, you get the sine times the sine of the angle times the hypotenuse is the opposite. And then we want to find the hypotenuse, so divide both sides by this angle. Can anybody see the problem here? Sorry, by the sine of this angle. By the sine of the angle, yes. You have a known fixed quantity, the radius of the sun, divided by the number you are trying to find, which is the distance here to its centre, must be the sine of half the angular size you want the sun to have. In this case, the sine of half of 0, which is the sine of 0. So you need a distance of the radius of the sun multiplied by 1 over the sine of 0 degrees, or 0 radians, whichever you prefer. So this is what a sine wave looks like. In effect, this is a graph of the height over time of a point on a rotating wheel. It's at the bottom, it goes up, it goes over the top, it comes back down, it's at the bottom, it goes up. That's cool. That's a sine wave. You may have seen these on oscilloscopes. You may have seen them all over the place. They come up a lot. 2.8 milliard in English, or billion in American, results. Sine waves are popular. This is a tangent curve. It's a rather different shape. I've marked the angle along the x-axis and the tangent along the y-axis, but I've also marked some angles up the curve here So you can see that, for example here, from 84 to 85 degrees, the tangent increases by 1 mouse cursor. And from 88.1 to 88.2 degrees, the tangent also increases by 1 mouse cursor. There is more difference between the tangents of 88.2 and 88.3 than between the tangents of 84 and 85. 89, 89.1, 89.2, 89.3. The tangent of 90 degrees is way off the top there. How far off the top? Well, conveniently, as far off the top as Grenfell Tower has to be away from you for its angular size to be 0. This is a graph of 1 over sine x. Remember, I said that if you want the sun to have an angular size of 0, the distance away it is has to be its radius multiplied by 1 over the sine of 0. It's a funky shape, and it's got some extra funky shapes on here because I forgot to set the opacity to 100%. It's these swoopy shapes here. And it's doing something rather strange there, and there, and there. This is in radians. So this x-axis is marked in radians, and I apologise for having the 0.05 and the 0.1 in it. Those shouldn't still be there. 2 radians. Pi radians is about here, and it goes off the top and reappears at the bottom. And 2 pi radians, it goes off the bottom and reappears at the top. If you zoom in and get the opacity right on a graph of 1 over sine x, down to 0.05 radians, this is about 6 degrees and this is about 3 degrees. It's not exactly, but it's close enough for me to just say it's about 3 degrees. The curve is just getting very, very close to the origin of the graph and disappearing off the top. Notice I have zoomed in on the x-axis, but out on the y-axis. 100,000, 200,000, 300,000. X is the angle in radians. Y is 1 over the sine of that angle. There's your answer. There is how far away the sun has to be for its angular size to be 0. And for 1 over tan x, the reciprocal of the tangent, you get a curve which is not the same as 1 over the sine, because the tangent curve isn't the same as 1 over the sine. But when you zoom way in on the angle axis and way out on the 1 over the tangent numerical axis, you get the same shape. I've zoomed in a long way here. 5 times 10 to the minus 5. 10 to the minus 3 is 1,000th. 10 to the minus 4 is 1/10,000th. 10 to the minus 5 is 100,000th of a radian. And it goes up off the top. Again, at x equals 0, 0 degrees equals 0 radians, equals 0 mils. At 0 angle, 0 angular size, the distance you are from Grenfell Tower when it has 0 angular size is that. And for anyone who doesn't recognise it, that right there is a symbol that means infinity. This, whatever it is, in this case 5, divided by this, has to be 0. For that to happen, this has to be infinity. For the sun, and for the tower, that divided by that is 0. Therefore that is infinity. So the next time somebody tells you that something can't be seen because it has gone beyond